Hello, and welcome to a digital lecture for Calculus 2 at Salt Lake Community College. In this video, we're going to go through 11.2, which is going to be the beginning of our discussion about series. Now, 11.1, we talked about sequences, which is what happens when you just get a sequence or just a list of a bunch of values in some numeric order. With series, what we're going to do is take those values in a sequence and add them all together and see what we can get. Now, we're not just doing it for willy-nilly just to add some constants together. What we're typically going to eventually turn this into is what happens when you add a lot of different functions together and what those functions can converge to. So, it'll be very useful down the line to even take some function that would be weird, even something like sine or cosine, and define that with a series of other functions. We'll eventually be able to define both sine and cosine as a sequence of a bunch of algebraic functions instead, which can be very useful for integration purposes. The main way in order to analyze a lot of the series that we're going to start with is by looking at what the partial sums of those sequences are. Partial sums basically just means that we're just looking at part of the sequence up to some point, usually up to n. And that's because when we're trying to evaluate the limits when we're trying to evaluate this infinite series of an infinite amount of numbers added up, we're really considering the limits as n approaches infinity of that summation up to some point n. This part here, the summation up to some n, this is a partial sum. It only sums the first n values, maybe the first 13 values, maybe the first 172 values, but that would be a partial sum. Hopefully, when analyzing these partial sums, we can come up with a formula that can help define this. And if we can, it'll be a lot easier to try to evaluate these series to see if they do converge or not. Overall, if we have a partial sum series, so if we have S of n, we know that the partial sums are convergent and they have a sum of s, so they're converging to some value s. Then that means that the infinite series that those partial sums come from will also converge to that same value s as well. So that's why it's going to be helpful to try to look at these partial sums. For example, here, show that the following series is convergent. We have 1 over 2 to the n, this series, which is the same as just 1 over 2 plus 1 over 4 plus 1 over 8 plus etc., etc., etc. What we want to do is see if we can come up with a formula that helps define this, and analyzing partial sums is going to be useful. S1 is just going to be the partial sum that adds up to 1, so that'll be the first value, 1/2. S2 will add the first two values, so 1/2 plus 1/4. That gives me 3/4. S3 will give me the first three values, so 1/2 plus 1/4 plus 1/8. That'll give me 4/8, 2/8, 1/8. That'll give me 7/8. Then I can keep going like this. Let's do at least two more. 1/2 plus 1/8 plus 1/8 plus 1/16. That one, if I have 1/16, I have 8/16, I have 4/16, or I have 2/16, I have 4/16, and I have 8/16. If I add 8, 4, 2, and 1, I should get 15/16. And then if I add the first five values, 1/2, 1/4, 1/8, 1/16, and 1/32, that'll give me 2 30-seconds, that'll give me 4 30-seconds, 8 30-seconds, 16 30-seconds. So 16 plus 8 plus 4 plus 2 plus 1, that should give me 31 over 32. And I can continue on with this trend. But what I'm noticing, though, if I look at the sequence of my sums, I have 1/2, 3/4, 7/8, 15/16, 31, 32. So 1/2, 3/4, 7/8, 15 out of 16, 31 out of 32. And what I'm getting is that this is converging, or what this is defining by, if I look at the denominator, this is still 2 to some power. I still see the 2 to the power on the bottom, But on top, what I'm seeing is 1, 3, 7, 15. It's basically that power, but I'm taking 1 away from it. Instead of a full 2, I have 1. Instead of a full 4, I have 3. Instead of a full 8, I have 7. So the top is just 1 minus the bottom. And since the bottom is defined as 2 to the n, I have 2 to the n minus 1. Or 2 to the n over 2 to the n is 1 minus 1 over 2 to the n. Therefore, when I'm trying to find the limit as n approaches infinity of the sum of 1 over 2 to the n, what I can do instead, as I equals 1 to n, what I can do instead is look at the limit as n approaches infinity of s sub n, which we confirmed is this, or 1 over 1 minus 2 to the n. And 1 minus 1 over 2 to the n, as n approaches infinity, this goes to 0. As n goes to infinity, this is just getting 1 over an infinitely large number. So this should be going to 0. So this is approaching 1 minus 0. This is approaching 1 as my answer. Therefore, I know that this sequence, this infinite sequence, this is adding up to a sum of 1. So that's how we use partial sums. We use partial sums. We found what those values were in those partial sums. We made a sequence of those, and we were able to define that sequence. Kind of a neat thing with this problem as well, because this is actually a pretty famous one. If you draw a 1 by 1 box, the partial sums here, if you just add the values in the sequence, you have 1/2 of the box full. That's what this first half means. And then you have another 1/4 of the box full. And then you have another 1/8 of the box full. And then another 16th, 32nd, 64th, 128th, etc., etc. This is starting to fill out a completely shaded box that's a 1 by 1 box. And 1 times 1 is 1. So, kind of a neat little example with that. Okay. Now, generally, if you are summing the terms in a sequence and it does indeed become convergent, then what that really means is that the values of the sequence of it, so if the series is going to be convergent, that means the sequence should be approaching 0. And we see that here, the previous values, 1/2, 1/4, 1/8, these values of 1 over 2 to the n are approaching 0 themselves. They're getting really, really, really small. However, the direction of that is very important. If we know a series is convergent, then that means the limit of the sequence is going to be 0. So the values themselves are getting smaller and smaller. That way they all are getting arbitrarily close to some overall limit. The unfortunate thing is this, which is called the Nth Term Test. This is not true in the reverse. We do not know that if a limit of a sequence goes to 0, that the series is convergent. This is not true. We cannot go the backwards way. We can only go in this direction. And we'll actually have an example in a moment of why that is. However, this nth term test, what we'll more often use it for is for its second clause, because it has 2 clauses. First clause says that if the series is convergent, then the limit of the sequence goes to 0. But the more important one, the second clause, says that if the limit of the sequence is not 0, so for example, if we had a sequence that went to some other value, I think the last one we did on 11.1 actually was bounded, but it went up to like 2.5 or something. If we have a limit of a sequence is going to 2 or something, then that means that the series of adding those will diverge. Because if all the values are approaching maybe 1, like the sequence is approaching 1, then that means what you're going to eventually be doing when you add them up is you're going to be progressively just adding 1 an infinite amount of times, which is going to go to infinity. So the second one is very useful. This is sometimes also why the nth term test will be sometimes known as the nth term test for divergence, because that is its main use, to try to tell if a series is divergent. Now, I was saying that you can't go in reverse for the first clause. You can't go from a limit equaling 0 to say that it's convergent. We know that if it's not 0, if the series, if the sequence is not approaching 0, then that means it diverges. But if it is approaching 0, we're not sure. It could diverge or it could converge. The previous one converged, as we already shown. This 1/2, 1/4, 1/8, if I had this sequence of values, these are all going to 0, and we show that this converged. But what we're going to show here in example 2 is a situation where these actually are divergent. And the sequence of this here, if I did the limits of 1 over n as n approaches infinity, that goes to 0, for sure. N approaches infinity, 1 over infinity is 0, yeah. However, this is not going to imply that the series is convergent. This is not going to apply that. Now, to show that with a harmonic series, what we're going to do is draw a lot of the terms out, and we're going to group these smartly. So, if I have, say, if I have a partial sum, the partial sum would be defined as 1 plus 1/2 plus 1/3, and all these terms. I'm going to go up to maybe the 8th term. Trying to give myself room for a reason here. And then if I'm going up to n, that means I'm eventually going up to 1 over n. Well, so far, it looks like I'm progressively adding less and less every time, but I'm trying to show that this is divergent, which means that this eventually goes to infinity, which seems weird. However, look what happens when I start to group some of these. I'm going to leave 1 and 1/2 as they are, but then I'm going to start to group some of them. Specifically, 1/3 and 1/4. Well, I know 1/3 is bigger than 1/4 because it has a smaller denominator. So, I know that this is going to be larger than if I were to replace 1/3 with 1/4 instead. I know that that is true. 1/3 is bigger than 1/4. So if I replace it with 1/4, I would get a smaller answer. There's a reason I did this. And I'll do this again for the next group. I'm going to do 1/5 over to 1/8, and I'm actually going to group 4 of these. And what I'm going to do is I'm going to show that it is greater than if I were to replace them all with 1/8. 1/5, 1/6, 1/7 are all bigger than 1/8. So if I replace them all with 1/8, I know that I'm creating a smaller summation, or a smaller partial sum. Now, why am I doing this? Well, look what you get from this. 1/4 plus 1/4, that's 2/4, otherwise known as 1/2. 1/8 plus 1/8 plus 1/8 plus 1/8, that's 4/8, otherwise known as 1/2. And I could continue this trend all the way up to 1 over n. Basically, what this means is I'm adding 1 plus an infinite amount of 1/2s up to really infinity. So I'm basically adding an infinite number of 1/2s. So this will diverge to infinity. If I add an infinite amount of 0.5s, I will eventually get to infinity. Slowly, but I'll get there. Now you may be saying, well, wait a minute, you're not grouping the same amount every time. You group 2 first, 4 the second, and if I go up to the next multiple of 2, because I saw 1/4 and 1/8, the next one will go up to the 16th. So I'd add 8 values from 1/9 up to 1/16 and replace them all with 1/16. However, that's not a problem because, remember, this is an infinite series. If I have an infinite amount of these, I can group these however I like. And no matter how many I use to group, I'm going to have an infinite more to work with. So I'm always going to be able to group a finite amount of these to create an infinite amount of 1/2 to add. This is why the harmonic series is going to be shown as divergent. Not all the other series do this, and if you try, you can't do this with the previous sequence. You don't get something like this. The harmonic series is a very weird one, but it's a very famous one. It's one that you're going to always want to keep in mind, not just in this section, but in really every section for Chapter 11. If you can show or compare something to the harmonic series, and you know the harmonic series is divergent, then we can usually show other things are divergent as well, as long as we know that it's always bigger than the harmonic series. Kind of like what we did back in section 7.8. Alright, so relatively common one, and this is also again showing why the Nth Term Test is more so called the Nth Term Test for divergence, because the last clause is the most important thing. Remember, the last clause says that if the limit does not equal 0, then the series diverges. That's a for sure statement. But if it equals 0, so you can also add to this, if the limit of a sub n equals 0, shrug. We don't know. We don't know what that implies. It could go to a convergent sequence or series like the example 1 did. These values technically go to 0, but this is a convergent series. Or they could diverge like the harmonic series. So that would be inconclusive. We're going to have later on some other tests later on that will help us if we run into some tests that are inconclusive, because there are going to be multiple different ways to analyze a series for convergence or divergence. Later on, we'll actually do another way of showing the harmonic series as being divergent using multiple other different methods. Now, what I'm going to do for example 3 is also show that this one is either convergent or divergent. And what I'm going to use just to do this are concepts from the Nth Term Test. So, with the Nth Term Test, I want to first see what the limit does. If the limit goes to 0, then I'm not sure. I'm going to have to test other things. If the limit does not go to 0, I can stop and say it diverges. But looking at this, if I look at n to the third over 3n to the third plus 2n squared, just looking at those values there, I should know that that's not going to go to 0, but we should be able to show this as well with limits. So if I do a limit as n approaches infinity of a sub n, so if I'm doing the limit as n approaches infinity of n to the third over 3n cubed plus 2n squared, well, what I can do with that, I can either do L'Hopital's if I want to, because it's not exactly conclusive, because if I go to infinity, the top's going to infinity and the bottom's going to infinity. Or a smarter thing I do, because I see all of them have a power of n to them, what I can do is multiply each top to bottom as by 1 over n cubed. And I can do the same thing to the bottom as well. We did a trick like this back when we did some stuff with tangents, or I think it was tanh, actually, back in 3.11. This will take n to the third, and it will be now 1. 3n to the third will just become a 3. And then 2n squared will be divided by n cubed, which will make this 2 over n. Now if I evaluate this as n goes to infinity, this 2 to the n, this goes to 0, because as n goes to infinity, 2 over n, or 2 over infinity, will go to 0. So this is approaching 1 over 3 plus 0, or just 1 over 3. Therefore, since the limit of a sub n equals 1/3, which is not 0, by the Nth Term Test, this is divergent. What I recommend with these as well, get used to writing a statement like that. Don't just stop here at 1/3 and assume the reader knows what to do from there. You need to show that you can analyze from your answer what this means. And what you should always do as well is cite what rule or test you're using. Because we're going to have, as I said, a lot of different tests to look if a series is convergent, divergent, etc. So make sure you always cite what test you're working with. You could have probably, even with this problem, just cited that once you got to 1/3, but this adds more context to it, making sure you understand exactly what the Nth Term Test does. So this 2 then went to 0. Okay. So I've said this a bunch of times, but I also have it here. We can't use the Nth Term Test. Oh, wrong marker. Highlighter. We can't use the Nth Term Test to really confirm convergence of a series. You can't do it for convergence, but you can confirm that it's divergent. If the limit equals 0, however, it's inconclusive. You need to test other things. If you do need to test other things, what can we test? We don't really want to go back and just use the first definition that we did on the first page. But we do have other things we can apply. And the first one that we're going to introduce in this chapter, before we go into some of the other tests later on, are what we call geometric series. A geometric series basically means that you're taking some value you start with. So maybe you start with the number 200. And every value in the sequence or the series to follow that are all just multiplied by some constant ratio. So maybe you have 200 and you multiply that by 1/2. So the next one would be 100. Then you multiply that by 1/2 and you get 50. Multiply that by 1/2, you get 25. Multiply that by 1/2, you get 12.5. Since you're multiplying every time by the same ratio, that's what makes it what we call a geometric series. These are defined by this equation. This is the general form of them. The sum from 1 to infinity of AR to the n minus 1. We say n minus 1 because we typically want to start with A and then start introducing factors of that ratio to follow. So again, like I did 200, and the next one I did 100 because I multiplied by 1/2, and the next one I multiplied by another 1/2, which gave me 50, and then 25, etc., etc., etc. That'd be an example of a geometric series. But the question is, okay, why is a geometric series important to look at? Well, let's show that. And the way we're going to show that is a little bit strange. What we're going to look at are partial sums. So if I look at the partial sum of this, this means A plus AR plus AR squared plus AR cubed plus etc., etc. Really up to AR, if I have just n, I guess it's to the n minus 1. Then, if what I can do here, this is kind of a trick to solve these. You won't need to memorize this, but this is a common method to solve these kinds of kind of strange summations. I see all these have R on them except for one of the terms, A. So let's see what happens if I took that entire summation and multiplied it by R. Well, I would just get AR plus AR squared plus AR cubed plus AR to the 4th. Notice I'm keeping them trying in line. Plus all the way up to, really I'll do this previous one, I guess. AR to the n minus 2 and then AR to the n minus 1. Then this R to the n minus 2 would become AR to the n minus 1. And this AR to the n minus 1 would become AR to the n. Because all these are going to be multiplied by R, and that's how I get all of this. Now the reason I do that is because I want to see what happens now if I take one of these summations I built and subtract away the other one. So I said this is kind of a weird process, but you'll see why we do this. If I take S sub n and I subtract away R times S sub n, what I end up finding is that I'll have AR canceling out that one, AR squared canceling out that, AR cubed canceling out that, AR to the 4th canceling out that, etc., etc. And all these will cancel up until AR to the n minus 1 will cancel out with AR to the n minus 1. which means if I do this, the only two things remaining are a minus ar to the n power. Now, I can try to solve for what the summation is, because this is now s sub n times 1 minus r equals a minus ar to the n, or, move this up here, summation of n equals a minus ar to the n minus 1 over 1 minus r. That should be a times r to the n, yeah. I can factor out an a from this and just have this as a times 1 minus r to the n over 1 minus r. Or actually, I don't even need to do that. I can just split this into two fractions right now. I can just have a over 1 minus r minus ar to the n over 1 minus r. Yeah, that's all I really need to do. Because now I can try to think about what happens as n approaches infinity. So if I have the limit as n approaches infinity of s sub n, well, I have a couple cases here. And the case will depend on what r is. If I have that absolute value of r is less than 1, so if r is less than 1, maybe it's something like 1/2 or 1/3. What this would mean is that the 1/3 or 1/4, the higher value would be on the denominator taken to an n power. This would go to 0. That's what that would mean. So if r was less than 1, this would go to 0, which means all I would have left is that this equals a over 1 minus r. Otherwise, if r is not less than 1, or absolute value of r is not less than 1, so it's not a fraction really, if it's an improper fraction, that means the numerator would be bigger, taken to an n power. This is going to go to infinity. So that means it diverges. That's what a geometric series does for us. Depending on what the ratio you're multiplying by, that will tell you if this is going to converge or diverge. The example I did before, where you start with 200, and I multiplied by 1/2 every time, that common ratio of 1/2, I already know that this converges, because that 1/2 is less than 1. That's all I need. That's what geometric series is. If we can rewrite something as a geometric series, then it's going to be useful for us. This result is summarized here. A series of the form like this is convergent as long as that ratio is less than 1, and it converges to a over 1 minus r. Otherwise, we say the series diverges. Notice that unlike the Nth Term Test, we both have a way of defining something that is divergent and also to confirm if something converges, whereas the Nth Term Test really was only useful to show if something diverges. Now we have a tool to confirm if something converges or not. It won't work for everything, but it will work for a lot of things. We're going to show a few examples of those here. Okay. So, again, remember we're trying to make this look like the sum of a times r to the n minus 1. We want to think about what the constant value is and what the common ratio is. In this case, or in all these cases, we're going to determine whether they're convergent or divergent. We have 4/3 plus 4/9 plus 4/27 plus etc., etc. So we actually don't have this already as a summation form. In order to do so, what we're first going to do is see if there's some constant a value that's multiplying all of these. Well, I see on top they're all multiplied by 4, so that's one thing. And the bottom, they're all multiples of 3, so I could probably pull out a 4/3 itself out of each of these fractions. So I should be able to rewrite this or if I have this as this is the sum of a sub n, that means the sum of a sub n here, I have this as the sum of 4/3. That's my value for a. And then I want to see what I'm multiplying by. Well, if I take out 4/3 from this, I have 4/3 times 1 plus 4/3 times 4 times 1 over 3 would give me 1/9, plus 1 over 9 would give me 4 over 27, plus etc., etc. This is looking like 1 plus 1/3 plus 1 over 3 squared. So what I see as a common ratio here is a 1 over 3 taken to an n minus 1. This would define that series there. I have that constant value of 4/3, and the rest of this is what happens when you take 1/3 to the n minus 1. And again, you can test that. 1 into n minus 1 will make that 0. 1/3 to the 0 is 1. 1/3 to the 1 power is 1/3. 1/3 to the second power is 1/9, etc., etc., etc. Now that we have this written more like a normal geometric series, we should be able to evaluate it. And since we see that r equals 1/3 is less than 1, we know that this is convergent. And what this converges to is a over 1 minus r, where a is 4/3, r is 1/3. So you get 4/3 over 2/3, or 4 over 2, or 2. So I have that this series, 4/3 plus 4/9 plus 4/27, etc., this sums to a total of 2. And that's what it takes. If it's a little bit more direct, like here in example 5, we actually just have the summation given to us. We just want to identify our pieces. Note that this is a k to the just a 1 power. We want to make this look like a times r to the n minus 1, or in this case, k minus 1. So if I just quickly rewrite this, k equals 1 to infinity, I can rewrite this by pulling out one of those 9/8. 9/8. And then I have 9/8 taken to the k minus 1. That way it looks a little bit more like what a is and what r is. However, in this case, since we have 9/8, or my ratio is 9/8, and we know that that is greater than 1, this diverges by a geometric series. And that's it. That's all it takes. Again, when you write that it converges or diverges, always also cite what you know that from. Like, what are you using? Because otherwise, that didn't take too much work. Example 6 is going to be similar. It'll just take a little bit more work to maneuver. Again, we look at our exponents. We wanted to make it look like a times r to the n minus 1, or again, in this case, k minus 1. And the bottom looks okay. I have a k minus 1, but the top is k plus 1. So the way I can rewrite that is by taking two of those 4's out. 4 squared times 4 times k minus 1. If I add those back together, 4 squared times 4 to the k minus 1, that'd be k minus 1 plus 2 is k plus 1. I'm just trying to make these exponents look the same. But now I have this as a summation, k equals 1 to infinity, of 4 squared, which is 16, times 4 to the k minus 1 over 7 to the k minus 1. Or, since those are both taken to the k minus 1, this is 4/7 to the k minus 1. So we know that this converges by geometric series. Since 4/7, the ratio is less than 1. And we know that this will converge to A, which is 16, over 1 minus R, which is 4/7. So that's 16 over 3/7. So 7 times 16, that'll give you 70 plus 42. So that'll be 112 over 3. And that's what it converges to. Kind of a strange number. A lot harder to try to determine if you did that by hand. Okay, one last one of a geometric series. We have this one looks a little bit longer. We have the summation of 3 to the 1 over 8 to the n minus 5 to the 1 over 3 to the n plus 1. Again, we want to make these look like geometric series, so a times r to the n minus 1 is what we're looking for. We don't have either of those, and we also have a combination of things. But since there's just a simple subtraction there, all we really need to do is split this up into two summations. I'll neglect writing 1 to infinity here, but I'll write that as 3, 1 over 8 to the n. This should actually be an n, I guess. Minus the integral, or the summation, of 5 times 1/3 to the n plus 1. Again, don't hop on it yet. Don't jump on it yet, because we need to make it look like this before we evaluate it. And so for the first one, I just need to take one of those eighths away. So take one of those eighths out, and I have 1 over 8 to the n minus 1. But for the second one, I have n plus 1, so I actually have to take away 2. So I have to take away 1/3 squared, so I have 1/3 to the n minus 1 remaining. Therefore, what we have is 3/8 times 1/8 to the n minus 1 minus the summation of 5 over 9 times 1/3 to the n minus 1. So both converge by the geometric series, since 1/8 and 1/3 are less than 1. And since these both converge, we know what they converge to. The first one will converge to A, which is 3/8, over 1 minus R, which for the first one is 1/8. And the second one will converge to A, which is 5/9 for them, over 1 minus R, which is 1/3. So that'll give you 3/8 over 7/8. The eighths will cancel. You have 3 over 7. The second one, you'll have 5/9 over 2/3. Some of the 3's will cancel. You'll have another 2 on the bottom. Times 3, you'll have 5/6. So this will actually converge to a negative number. 42 overall on the bottom. That's 18 minus 35 will give you negative 17. So this converges to negative 17 over 42. And yes, it's perfectly fine for it to converge to a positive or a negative number. It does not need to matter. It's not like we're doing an area here. It can converge to whatever number it needs to. Alright, so that's a couple examples using geometric series. The more you work with them, the more you'll recognize them and just get them into that form and check to see if r is less than 1. If it is, you're solid. Okay. Now, I have a couple other examples here, and these examples are going to show something a little bit different. They're still going to do geometric series, but in a different way. Here, we have a decimal, 0.3671717171, or 0.3671 repeated, so 71 is repeated. And what we're going to do is we're going to write it as an infinite series. We're going to find the sum of it and use that to rewrite the decimal as a ratio of two integers. Okay. So if I want to rewrite this, I'm going to group the things that I see repeated or not repeated. First I see 3, 6, and then I see 7, 1, 7, 1, 7, 1, 7, 1. The first two, if I want to rewrite these as fractions, 0.36 I'd write as 36 over 100. But then the next two digits, 7, 1, would be over to the thousands, 10 thousandths. So that should be 71 over 10,000. So I'll say 1, 2, 3, 1, 2, 3. The third one would be 71 over another two zeros here. 2, 3, 4, 5, 6. So that's over 1,000,000. 1, 2, 3, 4, 5. And I keep going on like this. 1, 2, 3, 4, 5, 6, 7, 8. Etc., etc., etc. So that's how I'd be expanding on that. Again, if you want to rewrite in this decimal form, what I'm really doing is 0.36 plus 0.0071 plus 0.000071 plus 0.1234567 That's what would make this summation number. So what we see then here, aside from that first number of 36 over 100, the rest of this looks like a geometric series. Because I have this 71 over something that's just being multiplied by the same ratio. In this case, it's adding another two zeros every time. So it's really multiplying by 100. So I should be able to represent all the terms after that as a summation from 1 to infinity of, I'm starting off with 71 over 10,000. That's the first value I see here. And then the next one I multiply by 1 over 100 to get all the succeeding ones. Therefore, I can then say that, all right, well, this 1 over 100 is less than 1, so we know that this converges by the geometric series, and what it converges to is 71 over 10,000 over 1 minus 1 over 100. We could do some algebra with that. I'll have 71 over 10,000 over 99 over 100. Some of those hundreds will cancel out with two of those zeros here, so we get 36 over 100 minus 71 over 100 times 99 is 9,900. If I multiply 36 times, in this case, 99, what I get is 3564. And then 3564 minus 71, that should give me 34. Wait, why do I have minus? These should all be pluses. Plus, sorry. Plus 34. Or plus 71 gives me 36, 35 over 9,900. Which you can simplify down. If you simplify this down by, say, dividing by 5s, for example, this should simplify as far as 727 over 1980. And that would be its simplified fraction. Now, what's really good about these is that if you're working on a problem like this, when you get your final answer as a fraction, put it in a scientific calculator. Do 727 divided by 1980 and make sure it does evaluate to 0.3671717171, etc. So you should always be able to check these relatively simply. But that's going to be the process here. Split this up into a sequence of fractions If there's some fractions that don't agree, separate those out like I did. But all the other ones that have those repeated values, that 0.71 repeated, that should always be some fraction multiplied by, say, 1 over 100 or 1 over 10, 1 over 1,000, depending on how many digits are being multiplied or being repeated. I had 2 digits here being repeated, so that's why I'd be multiplying by 100 every time, because it would take 2 digits over for the next couple to show up. If I was repeating 3 digits, so this is 0.712, for example, then I'd be repeating 3 times, so 1 over 1,000. But yeah, so that's how those would work. Last concept here is something called a telescoping, or sometimes it's called also a collapsing series. This is going to do something kind of similar to what we did with the what we did with the harmonic series, where we grouped some of these values together. But what we're going to see is that a good amount of these values are going to cancel out. It'll also be kind of similar to how I evaluated geometric series in the first place. What we're going to do is just look at a partial sum, and we're going to see what is going to end up being a lot of fractions. All these collapsing telescoping series tend to be a lot of fractions adding or subtracting up. And we should see a lot of them cancel out eventually, except for some. So let's see what this looks like. If I want to look up, I guess, S sub k, I guess it would be. So the partial sum for k. Well, then I would start off with k being 1. I guess this would actually have to start at 2 now I think about it. Yeah, this would have to start at 2. So k equals 2. So that's 1 over 2 minus 1 over 2 minus 1, which is 1. And then that would be the first set. Plus, if I plug in 3, I get 1/3 minus 1 over 3 minus 2 is 1/2. Then I get 1/4 minus 1 over 4 minus 1 is 1/3. You should start to see this pattern here so far. Then 1/5 minus 1/4, etc., etc. The last two terms, if I look at k minus 1, I'd have 1 over k minus 1 minus 1 over k minus 2. Give myself some more room here. And then the last term will give me, if I just plug in k, I get 1 over k minus 1 over k minus 1. Now, this is the elongating of the telescope. So this is where you have the telescope looks like this, and then you just expand it out really far. What we're going to do, though, is quickly collapse this, hence why it's also called a collapsing series. The reason we collapse is because we see a lot of these fractions show up. Specifically, 1/2 minus 1/2, gone. Positive 1/3 minus 1/3, gone. 1/4 minus 1/4, gone, etc., etc. All these are going to cancel out up into a point. I even see 1 over k minus 1 and k minus 1, gone. And based on the previous trend, k minus 2 would have come earlier. You can even test that if you want to see the previous term before this one. The only things that don't cancel out are this minus 1 and this 1 over k. So that means what I have is 1 over k minus 1. That's what this partial sum looks like. Therefore, I can say that the limit as k approaches infinity of this from 2 to infinity of 1 over k minus 1 over k minus 1, that limit is the same as the limit as k approaches infinity of the partial sum, which we found to be 1 over k minus 1. And as k approaches infinity, that goes to 0, so we have an answer of negative 1. So this overall approaches -1. That would be an example of a telescoping series. But let's do one more so you can see those. Those are a little bit tricky. Alright, so this one doesn't look like before, where it's just an addition or subtraction of fractions, but we should be able to split this up relatively nicely. What we're trying to do here is we're trying to find the limits, really, as k approaches infinity of this summation. Really, you could say, or let's say n approaches infinity, from 1 to n of 2 over k plus 2 times k. But I should be able to split these relatively nicely because we did talk a little while ago about how to do partial fractions. So let's do that. 2 over k plus 2 times k should equal a over k plus 2 plus b over k. Doing a little bit of work there, we have a times k plus b times k plus 2. That should equal 2 itself. Or a plus b k plus 2b equals 2. Therefore, b equals 1 pretty easily. And then a plus b equals 0. So that means a has to equal -1. So I now have this as the limit as n approaches infinity of the summation of a being -1. So if I guess I'll do the positive one first. I'll do 1 over k minus 1 over k minus 2. Again, so that was a 1, that was a -1. I just put the -1 second. Now, if I look at a partial sum of this, if I start with 1, wait, am I supposed to be starting with 1? Hold on. Yeah, because that's k plus 2, okay. So I start with 1 to n, or 1 to infinity. I have 1 over 1, so that's 1, minus 1 over 3, plus 2, I'll get 1/2, minus 1/4, plus 1/3, minus 1/5, plus 1/4, minus 1/6, plus 1/5, minus 1/7, etc. up to, I usually like to do the last 2 or 3 terms. So I'll do k minus 2 first. So 1 over k minus 2. And then if I add 2, I get 1 over k. Plus 1 over k minus 1. Minus 1 over k minus 1 plus 2 is 1 over k plus 1. And then lastly, 1 over k minus 1 over k plus 2. The more terms, the better, because then you can see what cancels and what doesn't, because they won't all. And last time we only had 2 terms remaining, but we're going to have more here. We see minus 1/3 and 1/3 will cancel, and that's going to kind of show the trend. So this one will cancel out with the first term 2 pieces later. So that means -1/4. If I go 1, 2 over, I see 1/4. -1/5, cancel out with 1/5, etc., etc. -1/6 will cancel with 1/6, -1/7, etc. But some terms don't cancel. I still have 1, and I still have 1/2 remaining. Later on, though, I start to see that trend show up again. I see minus 1 over k canceling with 1 over k. That 1 over k minus 2 would have canceled out earlier here, and so would have the 1 over k minus 1. Those all would have canceled earlier based on that trend that I saw, that the beginning terms are going to be canceled after this one. The only beginning terms that left over were 1/2 and 1. After that, the beginning term were always gone. But that's not true for 1 over k plus 1, 1 over k plus 2, because I never plugged in k plus 1 or k plus 2. I only went up to k. So those would have stuck around. So these 2 terms are going to be left over. And we have overall 1 plus 1/2 minus 1 over k plus 1 minus 1 over k plus 2. That is the partial sum. So now, if I look at the limits as k approaches infinity of that partial sum, I get 1 plus 1/2 minus 1 over 0, 1 over infinity, which goes to 0, minus 1 over infinity, which goes to 0. So I get 1 plus 1/2, otherwise known as 3/2. So this series is convergent and is converging to 3/2. All right, so that's hopefully a lot of examples of working with series, some converging, some diverging. Usually the trouble comes with it being converging. We had one or two examples earlier of divergent sequences, but those tend to be rather easy because if you show something is divergent using one of our methods, like we did here with example 5, it takes little to no time. The converging ones are the ones that take a lot more work, so I wanted to focus on those. But if you have any questions, feel free to put those in the comments below or ask your instructor directly. I hope you have a nice day.